Okay, so if we just said that one of the sources of magnetic fields are moving charges, then we should notice a magnetic field around an electric current. Okay, so moving charges create a magnetic field around them. So an electric field, no, so an electric current should have a magnetic field associated with it. And we see this because if we have a whole bunch of electrons moving, so if we have a high current, we're going to have a noticeable magnetic field around that current. Now, so there are some nuances about the way this magnetic field is formed around the current of wire. So the magnetic field around a current forms concentric circles around the wire. So it is concentric circles around the wire, and it gets weaker the further away you are from the current. So there's an actual mathematical model that kind of describes just what magnetic field strength is, and then we'll talk about kind of like what does it look like visually in terms of the magnetic field map. So the actual equation for the strength of the magnetic field near a wire, remember our symbol for magnetic field is the letter B, and so it is B is equal to mu naught. So mu, this is similar to our coefficient of friction and like our metric prefix of micro. So mu naught times I over 2 pi r. And what the variables are, the I, we should know that one. I is just the current. R is the distance from the wire. And mu naught, this is a new quantity, it's a new constant. Mu naught is the permeability of free space. It's very similar to our epsilon naught value that we saw with electrostatics when we had like the K equation. If you recall, K was equal to 1 over 4 pi epsilon naught, and epsilon naught was 8.85 times 10 to the negative 12. And we could just say, okay, well, that's just 9 times 10 to the 9, way it all shakes out. And this epsilon naught value had an effect on how charges could interact with each other. It was like, what is in the space between this charge and this charge? And we also saw the epsilon naught value with our capacitors when we were looking at, well, what is in between our two parallel plates for our capacitors? Is it just air, or is there some other dielectric material that allows me to store more charge on there? Okay, so the same thing is going to be with this mu value. This mu value is what is in the space between. So here I've got my wire, here's my wire, and I've got a current flowing upwards, and I want to know what the magnetic field strength is right here. Well, it depends on like how strong is this current. It depends on how far away you are from that current, but it also depends on like what is in between here. And if it is just air, we call that mu naught, and it's the permeability of free space. If it's a different material, then it's going to have a different mu value. And so there's like a list of different mu values you could have. And this is going to come into play a little bit later on when we talk about electromagnetic waves. But for now, for the problems that we're going to look at, we're just going to do mu naught, free space or air. And this has a value. Mu naught is 4 pi times 10 to the negative 7. And it's got some kind of funny units. It's Tesla, meters, over amps is the unit for mu naught, okay? So now I kind of want to talk about like this idea of like what does the field look like, and I'll show you an animation in a little bit. But I said that the magnetic field around a wire are these concentric circles, and so I'm going to get rid of my R value here. It is as if it's like going around this wire, and so the question becomes now, because like technically like that magnetic field line is coming out and then going in and then coming out and then going back in, and the question is it coming out like in this direction or is it coming out in this direction? Because it matters. The direction of that magnetic field matters because it's going to affect the magnetic force that we'll see, okay? So there is a common way of being able to describe the direction of the magnetic field around a wire, and it's called the right-hand rule. There's actually two right-hand rules in physics. This is going to be right-hand rule number 1. And so right-hand rule number 1 shows the direction of the magnetic field around a wire. And you have to use your right hand, so it's called the right-hand rule. Your thumb is going to point in the direction of the current. Okay, so there's kind of assignments here. So thumb points in the direction of current, so of I. And your fingers will then naturally curl around in the direction of the magnetic field. So your thumb goes in the direction of the current, and then your fingers curl around in the direction of the magnetic field. So for example, in my case here that I've drawn, I have a current that is going upwards. I know the magnetic field kind of forms these circles around here, but in terms of like the arrow, what that looks like, if my thumb goes in the direction of the magnetic field, it's almost as if, here's my wire, my thumb is pointing in the direction of the current, and my fingers are going to curl around it like this. Okay, so it's going to curl around it like this. So if I had to kind of draw arrows, it would be almost as if my arrows are going in on this side, right? Like they're coming around and going into here. This is hard to draw visually on a two-dimensional surface. And so in science, we have another way of kind of denoting that z direction. We could draw, I'm going to do it a little bit closer here to me, so I have more space. Another way that we could draw this is the magnetic field are like, they're coming out of the page here, they're coming out and then they're going in. They're coming out and then they're going in. And we could represent those coming outs with a dot and the going in with an X. So another way to kind of draw this magnetic field line on a two-dimensional surface is I'd have dots on this side and I'd have X's on this side. And these dots represent that on this side of the wire, my magnetic field is coming out, and then on this side, it's going in, okay? So the video is gonna shift now to show you a model, a computer model of the magnetic field around a wire and then also around a loop of wire. Okay, so this model, it's kind of a simulation, is showing how the magnetic field looks like around a wire that is carrying electrons. And so we know that anytime we have an electron moving, it's got a magnetic field around it or associated with it. And if you have a whole bunch of electrons moving, then you have a current. And so in this model, this current is traveling upwards, and you can see that the magnetic field is these circles around it. And so the kind of visual here, you can kind of see it's going around, and this is just showing this one spot, okay? And I can do a couple things. I can increase the current value, and if I increase the current value, then my magnetic field is going to get a lot stronger because collectively I have more electrons moving. More electrons means I have more individual magnetic moments that are contributing to the overall
magnetic field. And then I'm going to bring it down to a more reasonable number. And then it's measuring the magnetic field at this like box right here. And I can actually move that box. So if I move that box further away, you can see that right here, this value here is showing me the Teslas, the magnetic field strength of at that particular point. So at this particular point, it's got, I don't know, it's a really cool simulation, but it's got really janky symbols here. I don't know why they can't just use a superscript or an E. But at this point right here, it's 4 times 10 to the negative 8 Tesla. So it's pretty weak. And if I increase my magnetic field, if I increase my current, you can see how that value goes up. Or if I move that point closer to my wire, then my magnetic field strength gets bigger and bigger and bigger. Okay, and to the point where like the biggest I can probably make it is if I get it 5 meters away from my object and I ramp up my current to be 20. Now, something to note as well is changing the direction of the current is not going to change the strength of the magnetic field. So I'm going to click on that button. But what did it do? Look at it again. It changed the direction of the magnetic field. Okay, and that's going to be kind of important when we analyze a little bit later this concept of the magnetic field due to alternating current. So if I had alternating current, it would be like it's this direction, it's this direction, it's this direction, it's this direction. Like the magnetic field would be continually changing for alternating current as well. So kind of interesting visual of the magnetic field around a wire. Okay, so for this model, we're looking at taking our single like linear wire and looping it around into essentially a ring or a circle. And when you do that, you end up having a bunch of magnetic field lines in the center of your circle, and they add up to become a pretty strong magnetic field. And so if you were to increase the current that's going through the loop, then you increase the number of field lines inside here. You can see I can get more field lines. If I make the radius of my loop smaller, it actually concentrates them even more. So this is a way where we can create a pretty strong magnetic field. Ooh, there, it finally caught up. We can create a really strong magnetic field if we make our loop pretty small and increase the current through our loop. And in fact, that's just one loop. If you have a whole bunch of loops, then you end up getting an even stronger magnetic field down the center of your loop.
Okay, so we see that the magnetic field gets stronger if we take our wire and we loop it around, okay? So if we have a loop of wire, we tend to have, so here's my current. If I were to model my magnetic field here, and remember my thumb is going to go in the direction of my current, my fingers are going to curl around the direction of my magnetic field. If I kind of point my thumb in this direction, I see that to the right of the wire, it's going into the page. So it's like I'd have these X's here, and then on the inside of my loop, I'd have these dots because it's coming out inside the loop. And you can see here, it's going into the top and coming out. So I have X's here, and dots here, and X's here, and dots here, and X's here, and dots here. And what that does is it produces a really strong magnetic field inside of your wire. Now, that's for one loop. If you have lots and lots and lots and lots of loops, you can imagine, okay, you end up having a really strong magnetic field inside your loop, down the center of your loop. And this is something called a solenoid. So a solenoid, and I'll show the word in a moment. A solenoid is where you take a really long wire and you just coil it around. So that's what this is. I'm gonna come up, zoom in. I've got lots of turns on this thing. So what happens is I have a really strong magnetic field inside of the loop here, okay? So let's talk about that scenario of a solenoid. So that's how you spell it. A solenoid. So this is when you have a wire with many turns. Current flows through, creating a really strong magnetic field inside the solenoid. current flows through, it creates a strong magnetic field within the solenoid. And this is often called an electromagnet. And I will model this a little bit in class. I'll show you some examples of using a current through a solenoid to generate a pretty strong magnetic field inside of that. Okay? So when we think about our equation for the magnetic field, we have to take into account that this is a really long wire, and I'm actually looking at what is the magnetic field inside of this. And so the equation for a solenoid, for the magnetic field inside of a solenoid, changes a little bit from our mu naught I over 2 pi r equation there, okay? So for that, I don't think I have a board for that, so I have to just draw it on here. So for the magnetic field inside the solenoid can be represented as B is equal to mu naught, oh, I think it's a capital N, mu naught N I over L, where I is still our current, N is the number of turns, and L is like the entire length of the wire. And oftentimes when you are given a solenoid, rather than given like the number of turns and the length of the wire, you're often given what's called a turn density. So it's just like the number of turns per meter. And so then our equation would just become B is equal to mu naught N I. Okay. So this is how you'd figure out the magnetic field of a solenoid. So we're going to do a couple of examples of finding the magnetic field near a wire and then also find the magnetic field with a solenoid.